So it might be helpful to draw this yo-yo essentially. So we have two cylindrical discs. Essentially, this will be a cylindrical disc rather. This will be a cylindrical disc. And then they're saying that there's a cylindrical hub, kind of like this, connecting the two. And then if you were to consider what a yo-yo looks like, the string would simply be around this little hub here. So, and then it'll be going up like this, and then you have a motion down. So this would be what a yo-yo looks like from not the profile view, but a front side view. And we know that we're going to denote these two disks as mass sub one, and then we'll denote this hub as mass sub two. So we can say that mass sub one equals 0.050 kilograms, and that radius sub one equals d sub 1 over 2, or 0.075 over 2. We can keep it as d sub 1 over 2 because we can simply just substitute this into our formulas. And we know that mass sub 2 equals 0.005 kilograms, so 1 order of magnitude less, and d sub 2 equals 0.013 meters. And at this point, we can say that the mass, capital M, is going to be the mass of the yo-yo, and this is going to be 2m1 plus m2, or 0.105 kilograms. Excuse me. So again, this would be the mass of the yo-yo. And we have the moment of inertia of the yo-yo. We'll just call it y, mass of y, yo-yo. There's going to be 2 times the moment of inertia sub 1 plus the moment of inertia of that cylindrical hub I sub 2. This is going to be equal to 2m sub 1 divided by 2 times d sub 1 over 2 squared plus m sub 2 over 2 d sub 2 over 2 squared. And this is going to equal m sub 1 d sub 1 squared over 4 plus m sub 2 d sub 2 squared over 8. So to find the moment of inertia of the yo-yo, we're going to have to use this. So we'll have I of the yo-yo is equaling 0.05, 0.075 squared over 4 plus 0.005, and then it'll be times 0.013 squared over 8, and y equals 7.042 times 10 to the negative 5th kilogram per meters squared. So this actually is just the moment of inertia. This is not a solution or anything, but this is a very important value. At this point, we can use energy balance. So we can say that the gravitational potential energy of the yo-yo is going to be equal to the kinetic energy rotational of the yo-yo plus the translational kinetic energy of the yo-yo. And so this is going to be m, the mass of the yo-yo, times g times h equals half I of the yo-yo, angular velocity squared, plus half mv squared. And we know that angular velocity is simply going to be equal to v over r. So that's going to be y over the yo-yo, v over r squared plus half mv squared. And we know that v, now that we have all of our energies accounted for, we can solve for V. So V would equal I over R squared plus the mass of the yo-yo, and as a numerator, 2 times the mass of the yo-yo times the acceleration due to gravity times height, all to the 1/2 power. And again, R here is the radius of the yo-yo, and this is simply going to be d1 divided by 2, rather d2. The cylindrical hub is basically the length of the yo-yo, and the radius of the yo-yo will actually help us. The radius of the yo-yo will actually be 0.013 divided by 2, so half that distance of the cylindrical hub. And this is going to be 0.0065 meters. So V is equaling 7.042 times 10 to the -5th, and this will be times 0.0065 squared to the -1st. I just didn't, this is a kind of a neater way of writing it, plus 0.105, and then 2 times the mass of the yo-yo, so 0.105, acceleration due to gravity 9.8, and then the height of 1 meter, all to raised to the 1/2 power, and this is going to equal 1.078 meters per second. So this will be your answer for part A. 1.078 meters per second. Answer for part A. This is the speed of the yo-yo after it has dropped 1 meter. And so we can get a new workbook here. B is asking us for the ratio of the rotational kinetic energy versus the total kinetic energy. The total energy, whether it be kinetic or whether it be a kinetic or gravitational. This is going to be 1/2 I omega squared as of course as the formula for rotational kinetic energy. But now the total energy, we can say that the total energy is going to be rotational kinetic energy plus translational kinetic energy, but this sum simply equals the gravitational potential energy. So for the total energy, we can simply just say mgh. And this is extremely convenient because, again, omega equals v over r, and this becomes a lot easier. So ke rotational over E total is going to equal 1/2 of I V over R squared divided by mgh. And this is going to equal 1 over 2, and then 7.042 times 10 to the -5th, right? And then this will be 1.078 squared 0.0065 squared, and this will be to the -1st. So you'll have to divide that. That's why it's raised to the -1st. And divided by mgh. So m will be 0.105, g will be 9.8, and the height will be, again, 1 meter. And we find that the ratio of the rotational kinetic energy to the total amount of energy is going to be 0.941. So essentially, 94.1% of the energy stored in this yo-yo is due to its rotational kinetic energy, which makes sense because when you play with a yo-yo, when you throw the yo-yo down, it actually descends quite slowly. The linear velocity of a yo-yo isn't that great. However, when you see the yo-yo at the very bottom of the height drop, it is spinning extremely fast. So we can safely say that this is correct. The moment the kinetic energy, the rotational kinetic energy, the ratio of the rotational kinetic energy with respect to the total kinetic energy, rather the total energy period, is going to be 0.941. So again, 94.1% of the total system's energy is rotational kinetic energy. And that's the end of the solution. Thank you for watching.